The concept of, or at least the reason I use it, is that I think one possible explanation for why somebody would kind of goof this is this concept of density. Right? We don't do a really good job of wrapping our head around the density concept, and it's what relates mass to volume. So when we think about the feathers in a kilogram of feathers, like, oh, well, it's not that big of a deal, right? Because, a kilogram of feathers isn't going to hurt that bad because it's spread over a larger volume. We don't actually bring the volume consideration into it when we think about which one's heavier, right? Because for whatever reason, we're thinking of some other aspect. Ultimately, what density is it relates that mass to volume. Every substance has a particular density, and it is that density that we could use as a physical property to describe it. This is how we could identify gold back in the old days, because gold has a characteristic density that we could then identify a sample and differentiate it from gold versus, say, fool's gold. Okay? So it's kind of neat that we could use this. Okay, so if we look at it, density as a solve, okay, so here's an equation that we could theoretically memorize, and you may already have, that's okay, and I would argue you don't need to, okay, is mass over volume. Okay, well, what unit would you use for mass?
Grams.
Grams. Why would we pick grams? Why not pounds? We could really use any mass unit that we wanted. Typically, we pick grams for our mass, and for our volume, we typically we actually pick milliliters, okay, for it. And again, it's just because when we run the calculation with that mass and that volume, if we calculated that out, we would get a density value, okay, with those units of grams and milliliters. We would get a numerical value that is on the order of probably 20 to 0. Right? So the number that we calculate as a result of our density is now something that we as humans can deal with reasonably. If we picked liters instead of milliliters, well, that changes the number output, and we can't deal with that kind of easily. Okay, so that's the only reason we really pick those units, is the number as a calculation result is easier for us to process and hold on to. That's it. Right? The next big thing I kind of want to address with this is, well, what is density? Right? Yes, it's this physical property, but it actually is another thing. What is that other thing? I know we just had spring break and we're going to be forgetting all about what we talked about beforehand. What is this? This is a conversion factor. Okay? Density is merely a conversion factor that now allows me to relate the mass and volume. So I can convert a mass to a volume for that substance. I can convert the volume to a mass for that substance. So really all density is another conversion factor. Okay? Just like every other conversion factor we've dealt with. Okay? If we go through and look at the units, again, we pick grams and milliliters because typically when we look at a solid or a liquid, particularly water, when we look at the density for ice, it comes in about 1. When we look at the density for water, it comes in about 1 gram per milliliter. Notice that doesn't say milliliter, right? It doesn't say centimeters cubed. They're the same thing, right? So depending on which system we wanted to look at, we could use centimeters cubed or milliliters. When we move over to water vapor, now in the gas state, our units change a little bit. Why might our units change? Why did we pick, well, there was a phase change from solid to liquid. Why did we pick the phase or the units of grams and milliliters for solids and liquids?
Because you can contain them in a container.
When we massed those things out, that ratio came out to be what number? 1. Okay. If we go through and do that for water vapor, are we going to get a value close to 1? No. If I do grams, what's the mass of water in the gas state? It's going to be a really tiny number because in the gas state, each of those particles are moving really, really far away from each other. So the number that we would write there would be insanely small. It ends up getting so small that our human brains don't deal with it well, so we switch the unit system. Switching the unit system can now scale that number up so that it gets into this 20 to 0 range. Okay? So if we go through and take a look at examples, we've got our ice. Notice the densities, the units they're listing here are grams per milliliter. Those are referencing everything underneath. Notice again their range, roughly 0 to 20. We move to liquids. Okay? Grams per milliliter, again, 0 to 20. What happens when we move to our gases? Notice those are now closer to the 0 end of it, but what happened to the unit? We went grams per liter. Why would we do that?
To make the number bigger.
What would our number be if this was grams per milliliter? So I want grams per milliliter. Standard conversion. Are those things equal to each other? Is blue equal red right now?
No.
What do you need to do? I need to get rid of liters. Yeah, so liters I place in the numerator. What do I want in the denominator? Milliliters. What's the conversion between those? 10 to the negative 3 is what milli means. I place the power of 10
With the core.
the core unit. And what do I get for an answer? 1, 2, 3. Do I need another 0?
Yeah.
No.
1, 2, 3. Oh, I think I got it. Grams per milliliter. Can our human brains deal with that?
No.
Not very well. So what ends up happening is we switch the unit from milliliters up to liters so that now the number makes a little bit more sense. Okay, we're up to that 0.09. Okay? So when we go through and look at densities, you need to be a little bit careful with looking at just the numbers because the numbers can be misleading, which we've already talked about. Okay? The numbers carry absolutely no meaning. What carries the meaning is the units tied to those numbers. Okay? So watch out when you look up for densities for gases, almost always those units will switch on you to something else. And that's because the densities of gases are much, much, much lower than the densities for liquids and solids. Okay? That's all I really want you to recognize there. Okay? The next part would be interpreting density. So let's not do any math or more math because that was already a little bit of math. Okay? Let's interpret what those mean. Okay? I've got 3 solids and 3 liquids. Okay? Let's take a look at the solids. Which one is the most dense? Okay? In the picture. I don't care about the numbers.
Purple.
Okay? The purple one works. I would accept that. The other thing we could call it? Solid 3. This one ends up being the most dense. Why do we know it's the most dense? Because it's at the bottom. Is it because it's heavier? No. Heavier is a bad word. We can't use heavier in this case. Okay, we have to use density. All right? Which liquid is the least dense? The liquid now, L1, is the least dense. Okay? So these things just stack in order based off of their densities. What can you tell me between S1 and L1? Which one is more dense? Why is S1 more dense than L1?
It's at the bottom of L1.
It's at the bottom of L1. Does that make sense?
Yes.
How about S1 versus water?
It would be the water. This one is the least dense. But less
S1 is less dense than water because S1 is
above the water.
above the water. So if we just look at our image, our least dense is at the top, and it goes all the way down to our most dense. Yeah?
Yeah.
Okay. This can get nasty as a question because if you looked at the old practice exam, you didn't get tested on it on this exam. But if you looked at that practice exam, there was a question that listed a bunch of substances and their densities. What that question is asking you to do is to build this diagram. Once the diagram is built, you can then answer the question about where things fall within that sequence. It's just asking you to rank the substances via densities. Make sense? The last part of it, you got to watch out for top and bottom. And that's it. Okay? So, you guys want some help on a walkthrough?
Yes.
Okay. So if you're asked to solve for the density of a platinum nugget that has a mass of 224.5 grams and a volume of 10.0 centimeters cubed, okay, the list afterwards is looking at the potential units that we want to solve for. Okay, I'm going to argue that the grams per centimeter cubed one is too easy, so we're going to ignore that one. So we want to know the density in pounds per liter. Okay? Where a lot of people will instinctively jump all over, and I'm fine with this, sort of. They'd say, well, density equals mass over volume. Okay? And we might even say, well, it's written right there too. Let's say it wasn't written right there. Let's say you didn't memorize it. Could you solve the question?
Yeah.
Why?
You have pounds over liters.
Okay. Saying mass over volume I don't really accept because you're saying mass over volume, you knew density. I'm saying you don't know that. How could you answer it if you don't know what density is? What are you told to solve for? Pounds over liters. What is pounds a measure of? I don't accept weight officially, but largely because it has too many letters. Mass. Liters is volume. Okay. Oh my gosh, there's the formula for density. Okay. The units can tell you what you need to do. Use the units to allow you to go through and do the solve. We don't have to memorize that density is mass over volume. Okay? And I would argue is actually useless to memorize. Okay? So I want mass over volume. What information is given to me? The mass and the volume. Okay? So we could just start using them. Where should I place those? Okay? And I'm going to say 224.50 goes in the numerator is wrong.
Oh, wait.
And I know spring break was there, so you're like, what? Remember, this is me being a jerk because you're using numbers. I don't like numbers. What goes in the numerator?
Grams.
Grams. Why do I want grams in the numerator?
Because that's what you're starting with.
It's in the
Okay, and I like that answer, so I appreciate that answer. Most people would actually get this question correct as written. Interesting observation. I don't remember if that was the right number. What did I do? Switch the order of the numbers. Guess what happens to people getting the question right? Falls through the floor. Nearly everybody gets it wrong. Okay? Literally, the sequence of numbers of the given information causes you to get it right or wrong. Why? Because what are you doing?
We go by sequence.
We go by the sequence of number. Oh, that's the number that I was first given, so that must go in the numerator. Really? 10 centimeters cubed is a measure of volume. Where does my volume need to show up? In the denominator. Okay? So when I talk about the logic behind why you're placing the numbers where you're placing them, this is exactly what I'm referencing. So thank you very much, Cody, for going through and saying that statement that made me trigger on that. All right? So when I go through and solve now, it's up to me to decide where I want to place my mass and volume and which of those numbers I want to start with. All right? But I need to make sure I know why I'm placing them in those locations. Does that make sense? Okay, so with that said, what do you guys want to start with? Grams. Where should what is grams a measure of? Mass. Where does mass need to show up in my answer?
Numerator.
In the numerator, which means in my calculation, grams needs to show up in the numerator. Okay? Am I given just grams in the question?
No.
I can see that as a valid answer to my question, but that is not the question I wanted to ask. Is the numerical value associated with grams associated with any other unit? No. Right? It says 224.5 grams. Done. That is a single piece of information. Which means, what is the unit going into the denominator? Nothing. I don't want any unit going down there. I want that to be 1. I don't want to change the meaning of the unit above. Okay? It is a given piece of information. We're going to now use 224.5. I don't know if that's right or not, but let's just use it. Okay? This now puts mass in the proper spot. Okay? What do you guys want to do? Do you want to bring volume in yet, or do you want to fix the mass? Let's fix the mass. Okay. What needs to happen to the mass?
Turn into pounds.
It needs to become pounds. Do I know the conversion factor between grams and pounds?
Yep. Yes, it says you right there. 1 pound equals.
Okay. So what do I need to write?
1
1.
in the numerator.
I don't accept numerator.
1 pound.
1 pound,
And 454 grams.
454 grams. What happens? The grams cancel. I would now have pounds in the numerator. Is that what I want?
Yes.
Yes. Okay. This is where you'll get some people splitting it into 2 solves. I would argue again, we don't have to split it into 2 solves. The reason we're splitting it into 2 things is because you've memorized a formula. I haven't memorized a formula. I know liters needs to be in the denominator. Okay. So does the left equal the right yet? No. So what needs to happen?
You need to add the centimeters cubed.
I somehow need to get my volume inserted into this. Am I given a volume?
Yep.
Yeah. What volume am I given?
10 centimeters cubed.
I'm given centimeters cubed. Why am I placing that centimeters cubed in the denominator?
That's what the answer means.
That is a volume. That is where my volume needs to be. What number goes with that centimeters cubed?
10.0.
Okay. What number and unit needs to show up in the numerator? 1. Why? I don't want to change the meaning of that 10. Okay? That is a given piece of information. This is a distinct given piece of information. I am keeping them separate in the equation. Okay? Is centimeters cubed the same thing as liters? No. So what do we have to do?
Convert it.
We have to convert it. Ideally, what happens in our conversion?
Cancel all centimeters.
Centimeters cubed gets canceled out, and we get liters. Do we know that conversion?
No.
Okay. I heard a no. We're sticking with that. What conversion do we know?
Milliliters.
We know milliliters. What is the conversion between those? 1 to 1. Okay. Centimeters cubed cancels, and I would have milliliters. Milliliters what I want? What has to happen?
Convert it to liters.
I have to convert it to liters. Do I know that conversion factor?
Yes.
Yes, that's one I'm required to know. What is that conversion factor?
10 to the negative third.
10 to the negative third is what a milli is. That goes with the core unit. What happens with my units? Milliliters cancel. If I ran and looked just at the units, what unit would I be left with in the numerator?
Pounds.
Pounds. What unit would I have in the denominator?
Liters.
Liters. What does that mean?
Pounds per liter.
I now have my answer. I can punch it into the calculator. Make sense? Okay. We're just going to do an end run on this because I'll usually get people asking, couldn't I have just written 224.5 grams over 10.0 centimeters cubed and then done the rest of those conversions? Yes, absolutely. I have no problems with that. That is perfectly valid. Okay? But what you have done is you've combined 2 pieces of information. You combined them correctly, but why did you combine them? We would know that we could combine them that way because we know density is mass over volume. Either because it was given to us or we memorized that formula. If you want to memorize it, that's okay. Okay? So Cody and then maybe Alex.
When you're doing that, what the issue be like? You're trying to still get pounds over liters. And that's just by dividing that.
You still end up going through and doing the exact same conversions.
Oh.
Yep. All that's happening here is we're combining the two things in blue into one calculation.
All right.
The question that I encounter is, or that I ask, is then why are you doing that? If you're doing that because you didn't like having it over 1 or having 1 there, then I'm going to say no. That was a bad idea. If you're doing it because you know that density is mass over volume, and that's mass over volume, then legit, fine, you're doing it that way. But the reason you're doing it that way is that you memorized that. Okay? If you haven't memorized that, you can't do that. That was a lot of that. Make sense? Does that get where you were going to, Alex?
Yeah, well, I meant you get the density right there.
Yes. Yep. So we'd have to have that information either in the back of our brain. That's why I'd initially erased it, and then I left it up there at the same time. Because, yeah, it was written right there, too. Okay, questions about that? Okay, because I worked through one with you, in theory, 224.5, yeah, cool. If you enter that in the calculator, I believe you're going to get 49.44. Okay, we got a confirmation on that.
Yeah.
And sig figs, would that be correct?
48.45 is
Pounds. I already forgot it. Liters?
Yeah.
Okay. I heard a suggestion that actually with sig figs it's going to be 49.45 pounds per liter. Does anybody want to confirm that? Anybody want to deny that?
Seems like a lot.
I think the number is numerically correct. Sig figs is wrong. Why is it 49.4?
Multiplying and dividing is the least.
The fewest number of sig figs. When we go through and look here, you might be saying 2 decimals because it says 50. This is a multiplication division, so I don't care about the decimal places. But that one has 5 sig figs. But the other one has 3 sig figs. So the answer should actually go to 49. Oof. I'm going to fix it. 49.4 pounds per liter. Got it? Okay. Okay, your turn. Try and figure it out. An automobile battery contains, 1,275 milliliters of acid. If the density of the battery acid is 1.84 grams per milliliter, how many grams of acid are in the automobile battery? This is a slight flip on it, but you should still be able to go through and do it. Try and set it up. Immediately starting to write down information that was given. I'm back and forth on that one, and I think I kind of accept that. So we could go through and say, well, I'm given this, and I'm given this. I would argue the instant you see that little slashy thing, you should stop copying that, because that's not useful. Right? When you look at your exam, that slashy thing shows up with distances, and kind of the distance of converting, say, miles per hour, kilometers per hour. A lot of people screwed that calculation up. Why? You did the stupid little slashy thing. Okay? Because you didn't fully process what it meant. What it means is this. These are your 2 pieces of given information. The question is now, what do we do with those given pieces of information? Well, what am I solving for? What am I solving for? Grams. Okay? I'm solving for a mass. Okay? In our process, we would say equals grams. That's step 1. Okay? And the walk around the room, I didn't walk that long. I saw a lot of this, and I'm on the fence on that. And the reason I'm on the fence on that is you're wasting your time sort of rewriting the question, because you already have the question. The PowerPoint slides are given to you. You print them out if you want. Pull them up on a computer. Rewriting it because you're just rewriting the numbers out, okay, I kind of accept that because that makes sense. Okay? But step 1, what do I want? I want grams. Okay? And I even got a weird look because as I walked around, I was like, good job. That's exactly what I wanted to do. Like, what? All I wrote was grams. Yeah, that's a pretty huge first step that nobody else did. Identifying what you want for an answer is a pretty good thing to do. So get it down there. Okay? I now know where I need to go. I can go back and look at my given information and say which of those pieces of given information would be useful for me. Both eventually. Okay? Which one is probably the most useful right out of the gate? The one with grams in it, because that has what I want as an answer. Okay? Where do I want that gram unit to show up in my answer? In the numerator, which means when I take that given information and I put it down into my solve, I want grams to show up in the numerator. Okay? But I'm not given just grams, I'm given grams per milliliter. Now that I've got the units down, I can put in the numbers. Cool, grams, numerator, exactly what I want. Is that my answer? No, because I screwed up and put milliliters in there. Okay? What do I want to happen? Deleting it doesn't work. You can't do that. Okay? It was given as milliliters. You have to keep that there. Okay? What do I want to happen? I need another step. In that other step, I want milliliters to cancel so that those can now cancel out. That's cool. Am I given just milliliters? Yes. So now I can write in that number. What do I want in the denominator? All I want is 1. I don't want anything else there. And if I look at the given information, what is in the denominator? 1. Perfect. It aligns. Milliliters cancel. Punch in the calculator. I'm done. Really? That's it? Yeah. Yeah, we'd have to worry about sig figs. I don't even know what that... Someone get an answer on that?
Yeah, so it'd be 2,350.
2, 3?
20.
2,300?
Yeah, because
Oh, yeah, no.
when you get the
Okay.
calculator, it's 2,346.
2,346. Okay, how many sig figs is that? 4. How many do we need? 3. So I can keep the 2, the 3, the 4. I can't keep the 6, but the 6 is larger than 5, so I add 1, which makes that into a 5. And I get 2, 3, 5. That 0 is not significant because there's no decimal point. So cool, there's our answer. 2,350 grams. Make sense? Okay. I would not be surprised if other people did it too. Okay, but I will see people go through and do things like, well, there's X gram. Is that what I wanted? Yeah, X grams per. I have such a hard time doing it this way. 1,275 milliliters equals 1.84 grams per milliliter. Okay, and doing cross multiply. For those who are saying what, then close your eyes, stop looking at it. Okay, for those being like, yeah, I do it that way. There isn't necessarily anything wrong with that process. Okay? The issue is it is a single conversion. When I ask you to do multiple conversions, you're dead in the water, or you have to do a whole bunch of these conversions. To get that, you have to know each of those individual steps. That's a lot of work. Okay? That's why I'm telling you to not do that. Not because it's wrong, it's because its scalability isn't there. Okay, you can't build more things. Okay? Okay? Do we have to have heard of a unit to use it? No. Okay? This is one of the things that's very powerful about this conversion process, is we don't have to have any concept of what the hell a meek is or a stup. Okay? But I can still convert them. Okay? Assuming I'm given a conversion factor. Okay? And as silly as that sounds, that's exactly what we're doing in the next unit. It's the goos and the moos. Or the mucks and the somox. It was somox, I think. Somox and momox and all that fun stuff. A lot of people, oh, that was confusing. It was a lot simpler than saying moles of molecules of, it was another M1, magnesium. Okay? We're coming up with some way to simplify and boil these down to allow us to do these conversions easier. Okay? That's the point of the conversion system. Do we need to solve this one?
Yeah.
I heard a no first, so I'm going to do that one. Little country ball thing about France and the U.S. dealing with maps for a tank, plans for a tank. The conversion process is such a big issue that the U.S. was like, hey, we can make money by making other people's military equipment. Go figure. Okay? And so let's go through and do it. So we just need the plans to be able to build it. We look at the plans aren't in the metric system and not in the American system or the imperial system. So what do? Meh. I don't need to make millions of dollars. I just won't worry about it. I'll let somebody else do it. Okay? Because the cost to retool our facilities is so exorbitant that it didn't make sense to actually go through and build it. Allegedly this happens. Who knows? It's the internet. Okay? What?
The last image, he's so sad in the back. Like, he's like, what did I do?
See, conversions make other people sad, not just you.
You heard that joke, there's only two kinds of countries in the world that use the metric system, and those have been the moon.
Except China just disproved that. And the other one that's fun about that one is we actually use the metric system to go to the moon. We adopted our system into the metric system to go to the moon. So yeah, that's a fun system. So temperature, entirely different system. So we'll deal with some energies. Temperature is a measure of the average kinetic energy in a sample. Okay, so it's not everything, but it's the average energy. Right? There are 3 different temperature scales. Why might we have a whole bunch of different temperature scales? Why not just one universal one?
Made in different places, different times.
Different places, different times, and ultimately even different purposes. Kelvin became a little bit later when we figured out that these scales were based off of a system that wasn't universally applicable into science. Okay? So because we've got these different scales, of course we have to deal with different systems behind them. Okay? If we go through and look at kind of the standard numbers that come from them, Fahrenheit, I don't even know these numbers. Water freezes at 32 and boils at 212. Why did we pick 32 for a freezing point for water? That seems like a really weird scale for Fahrenheit.
That's 0 Celsius, right?
0 is the freezing point for Celsius, but why did Fahrenheit not pick 0 for water? Fahrenheit's world view was a little bit larger, and he noted that there were things colder than ice. And the coldest he could measure was 0 degrees Fahrenheit. So he built his scale saying the coldest he could get was 0 degrees. Ice just happened to be at 32 from that 0 point. Turns out his 0 point wasn't perfect because we could get a whole lot colder. Okay? But that's why that scale is so kind of weird with those numbers, because his 0 point was just the lowest temperature he had access to. Okay? That's what he established at the 0. It just wasn't 0. Okay? Why did we not just say, well, then that's dumb, we should stop using it because your 0 point's false? History was used long enough that we kept it. Okay? Celsius picked the 0 point for water. Why would we pick a 0 point for water? Water is so common. Okay? So it has to do with what we have access to and what we see around us. Celsius' 0 point was water because water was everywhere. He figured everybody could get a hold of water and even solid water. So we could see those values. When we look at Kelvin, Kelvin is the absolute temperature scale, which is kind of what Fahrenheit was fishing for. He just picked the wrong 0. Kelvin gets to an absolute 0. There is nothing lower than that 0 point. Right? That 0 point is pretty awesome because that means all temperatures in the Kelvin scale are positive. I don't have to deal with minus signs because minus signs are the devil. Okay? That becomes all sorts of problematic in Fahrenheit and Celsius when we run calculations. It becomes problematic when we look at oxidation and reduction. Okay? Those minus signs are a pain to deal with. The science temperature scale removes that. Okay? That said, everybody would look at you funny if you went through and said, well, it's 273. Okay? We aren't used to that temperature system. Okay? There is a typo on here. Because Kelvin is an absolute scale, it is not degrees Kelvin, okay, which is a very subtle thing to note. Don't stress about it. It's just Kelvin. There's not a degree symbol there. Both Celsius and Fahrenheit are degrees, okay, because they aren't off of an absolute scale. Okay? Temperature conversions, of course, because they're based off of kind of random appearing observations, the conversions between them are not the most pleasant. Okay? These happen to be the simplest versions that I have ever used. As far as memorization goes, you need the bottom one. Okay? You need to know how to convert Celsius into Kelvin. Okay? What you need to memorize is that you add 273 to Celsius and you get Kelvin. Okay? Because everybody asks, or somebody will ask about it. It says 273.15. Okay, can somebody tell me what pi is? Okay. Did everybody just hear the string of numbers she just listed out? Because I heard that, and I was like, what's that? I got 3.14. 15, yeah. What is she doing? She's overachieving. This is my overachieve. 273.15. Right? That's it. That's the only reason why the 15 is there. When I memorize that conversion, 15 goes into it. I don't know. Okay? That's all it is. All you really need is 273. Why just 273? Three sig figs. Okay? When we go up and look at our conversions between degrees Celsius and Fahrenheit, I will give you the top one. Okay? That will be given to you on the exam, and in fact, it's already been given to you on all of the exams so far. Okay? However, all that is a plug and chug, so what I will ask you to do is to convert Fahrenheit to Celsius. Okay? That one I won't give you. So how could you possibly do it?
Take the other side of the equation.
You use the algebra of the one above, okay, to get the other one. Okay? And if you need help with that, that's okay. That's ultimately all of our conversions has been doing that algebra process. Okay? So it's just a question of plugging in the values and switching things around to get there. Okay? Kind of makes sense? Cool. So that's temperature. You guys want to do it? Sure? Go for it. Body temperature is 98.6 degrees Fahrenheit. What is body temperature in degrees Celsius and in Kelvin? Okay. Another interesting observation. If I just went through and did this, Celsius. It's all right. I'm going to bet a lot more people get the question wrong. Just so you know. I want temperature in Kelvin and in degrees Celsius. All right. Do what you gotta. Solve for it. And because ultimately this is just plug and chug, we'll go through and talk through it right now. I did do a subtle switch to the question. That subtle switch to the question is oftentimes enough to get people to get the question wrong. Right? Because what you end up going through and doing is saying, well, what do I need to solve for? Kelvin. Why did you say Kelvin? It came first. How do you solve for Kelvin? By finding degrees Celsius. But because I said Kelvin first, what typically happens? Which ends up being wrong. Right? So be careful about the order in which information is given. Okay? We tend to kind of lock in and just run under the assumption that because it's given in that order, we need to use it in that order. That's not necessarily the case. Okay? And that's what we did back with the conversions. The same thing needs to happen here. Okay? So that is a wrong statement. To go through and solve for Kelvin, it's 273 plus our degrees Celsius. Do we have the degrees Celsius?
37.
We don't have it yet. Thank you for doing the math that fast, which I'll get to in a second. The equation we would use would be that guy up there. Fahrenheit 98.6. Oh my gosh, minus 32. 5/9 equals degrees Celsius. We enter that in the calculator and we get 37. Comes out flat 37?
Yes.
Okay. 37. I'm going to deal with that in a second. And really the reason I'm going to deal with that in a second is I don't know how to do it right. So 273 plus 37. 310. Okay, and that would be our Kelvin. And that would be our degrees Celsius. And because someone actually started to suggest it, anybody catch what they were suggesting? Sig figs. We have addition and subtraction through this calculation. Okay? Or addition, subtraction, and multiplication division, which means the sig fig rules go all sorts of nasty sideways on us. I don't like dealing with it, so I don't ask.
That's just going off the original.
Are we okay with that?
Yeah.
Yeah, I think usually what I would do is just run off of the original, keep it at 3 sig figs, just because. But ultimately, I don't really ask sig figs when it comes to temperature, because I am a bad person. Okay, heat. Okay, heat similar to temperature, but different concept. Okay, temperature measures the average energy of all the particles. Heat measures the total energy of all the particles. So while the average in the class right now might, what did I say, 72? 72. The total points in this class is not 72. Okay, the total points in this class is a lot higher. Right? That's what we're looking at with temperature versus heat. Heat is the total energy. Temperature is the average energy. Okay? Heat is measured in different units, in joules or calories. You did a heat lab, right, with the nut and the burning, calories, joules, that kind of fun stuff. Okay, so there are ways that we can represent and calculate that energy, and ultimately it's through energy transfer. Okay? Yeah. Every substance has a particular response to heat. Okay? Meaning if I add a certain amount of energy in, say a calorie, into a gram of that substance, the temperature change is going to be different. Right? So what we can go through and do is flip that around pretty much and come up with something known as a specific heat. So I look for a standard temperature change and a standard mass, and I say, how much energy do I have to put in to cause that temperature change? Okay, that is now the specific heat. So specific heat is how much energy do I have to add into a gram of a substance to make it go up by 1 degree Celsius. That's it. Right? The numbers that you end up seeing out of this and might explain why we invented the calorie unit as a measure of energy. Okay? What we're representing with these numbers are the specific heat for water, our most common phase. Okay? Why would we have invented the calorie unit? Because we wanted that temperature change, the amount of energy I put in, and that temperature change and all that to balance out to give us what magical number? Rhymes with fun. And it's also on the board. 1. That's why the calorie unit was... That totally... How is that not rhyme?
Fun and one rhyme is the sound of the spell.
Fun and one rhyme. Whatever. We can talk about it. I'll talk to my English people about it. Try it. What English people? I teach with an English person. It's okay. So 1 calorie per gram degree Celsius. Okay? Joules is another energy system that we can use. In that case, it's 4.18. Why? Because that's what we wanted to use for that energy representation. Ultimately, what have we written up there? A conversion factor, which means we can convert. Yes, exciting. We can do all sorts of calculations dealing with all this fun stuff. And we can do all those calculations starting in like 32 weeks in 151, and we don't worry about it at all in this class.
Great.
Yeah, cool. However, I do want you to be a little bit cognizant about what those things mean. The larger the specific heat, the more heat is required to raise the temperature by 1 degree Celsius. Okay, so what could I do with that? Which of the following substances is expected to have the largest specific heat? I don't see any numbers. That looks kind of rough. How could I possibly come up with that?
Each one has
So mass, true. So I could start to bring in mass into this. Do I know the degrees Celsius? No. Do I know the energy term? No. So while you could come up with a mass, I'll grant you that. I don't have any of the other information. What did specific heat mean again? To make the thing go up by 1 degree Celsius. So if I stick a match under this substance, it's providing energy. That energy then causes the temperature to go up by 1 degree Celsius. Okay? Do I know something about my elements that might dictate the ability for the temperature to go up or down when I add, or not down, but modify how the temperature goes up when adding heat? Metals conduct heat, which means when I add a match to the bottom of them, what happens to the temperature? It goes up very, very fast. Why? Because they conduct heat. I put in a very small amount of energy and the temperature goes up, which means my specific heat for my metals will be very, very low. Small amount of heat, large temperature change. So if I want a large specific heat, this means I have to put a lot of energy into it to cause the material to go up. That would be a substance that does what with heat? Absorbs it or insulates? What materials insulate heat? As a hint, it's not metals. Non-metals. Okay, all the way back to Unit 1. Remember we talked about all those properties? Yeah, here it comes back to bite you. Okay, you have to know them. Okay, so when we go through and look at this list, what are we looking for? The non-metals. So really all the question is asking which of these is a non-metal? Carbon, there's your answer. Wow, that was a really easy question. Once you process through all of those smaller questions to work up to it. Remember how I said it's the smaller questions that you need to deal with? That's what we're working towards. We need to deal with those smaller questions. Make sense? Okay. How else is the question made more difficult?
Put in different, or they're all metal.
They aren't all, I could make it more difficult. I'm saying the question specifically right here. How is this question actually made more difficult? Some are symbols, some are names. So when we look at the periodic table, yes, we can tell metals and nonmetals because of the staircase, but those are only symbols. Were you given only symbols?
No, you were given.
You were given some names as well. So you also have to know nomenclature to answer the question. Yeah?
Yes.
It's like a huge Unit 1 question. Okay? How could I change the question, which is where you're getting at? Instead of it being largest specific heat, I could ask smallest specific heat. Could I provide all metals or all nonmetals? No, that one I won't ask. Okay, and the reason I won't ask that is it's not a perfect trend.
Yeah, and then you have
Okay.
to memorize.
You would actually have to have specific heats memorized. Okay, so when I go through and build it, I make sure to pick elements that it aligns appropriately. Okay, and as a general observation, your metals tend to have smaller specific heats than your nonmetals. Okay, conservation of mass. Ta-da! We conserve it. We've already kind of addressed this when we balanced out chemical equations. I do want to address kind of one thing at the bottom because we can deal with this numerically. I give you 2 grams. Don't worry about balancing or numbers necessarily. And 1 gram of oxygen. How much gas was produced? Okay, there was a little bit of a pause there, so let's backtrack. 2 grams of hydrogen, 1 gram of oxygen, how much water was produced?
3 grams.
Right, you got that? Yeah, okay. And Owen's like, I didn't get that. Well, now's the time to ask. You got it? Okay. So, 2 grams, 1 gram, how much water did you make?
1 gram.
Why is it a little slower this time? Why is it not so cut and dry? Yes. There's 2 products. Yes, conservation of mass means the mass on the reactant side must equal the mass on the product side. In the previous equation, there was only 1 product, which means I just add up the masses. Why has the next one become so much more difficult? There's 2 products. I don't know the distribution in those masses. Okay? So we can use conservation of mass numerically really easily in combination and decomposition reactions because there's only 3 pieces typically. For the other reactions, they tend to get a little bit more complicated. For me to ask the question, how much water was produced, what do you also need to know? How much gas was produced? How much water was produced? 2.5 grams of water. Everybody got it? Cool. Mass and energy, Einstein says they're the same. Enough. Okay? And we run into another math equation which we could go through and solve a bunch of numbers in. Does anybody want to do a bunch of numbers? No. Shh. No. I don't want to do a bunch of numbers with them, so we won't worry about it. If you move into 151, you will have to deal with numbers with E equals mc squared. Okay? They become a little bit more challenging because almost all of them are powers of 10. Okay? But really what we come from or come back to is the law of conservation of energy. Okay? And we're identifying the different forms of energy. There's 6 forms of energy as far as chemists are concerned. What might those 6 forms include? Light. Heat. Temperature is heat. Electric. Mechanical. Nuclear. Chemical. Sweet geez, guys, the last one. Okay? Those are all our different forms of energy. Heat's probably the most important and the most dangerous, the most painful to deal with, okay? Because virtually all of the transitions between these result in the formation of heat. So when we talk about the efficiency of a combustion engine or the efficiency of lights or anything like that, it almost all comes back to the fact that we are losing energy in heat that we didn't actually want. Okay? When you turn on your car and you're using, if you're assuming you're using gas to power your car, okay, you're trying to use that chemical energy to turn into mechanical energy to cause the car to move. Okay? At the same time that that's happening, what else is happening?
You're losing heat.
Some of that energy is getting released as heat. That heat isn't being used to do anything except heat up your car, and that's it. Okay? Which is why you lose efficiency behind that process. This is why the combustion engine stalls out, no pun intended, 40-50% efficiency, I think. It might even be less than that. And a lot of it is due to that heat loss. Okay? We can adjust the system to make sure we don't get heat lost as much as possible, but the amount of stuff we have to go put in to cause that to happen ends up not being beneficial or cost effective for us. So when we talk about energy, that's pretty much our driving force for everything we deal with. Okay? And we want to shorten the leaps between any one of those. So to get the lights in this room, what do we have to do? Where are we getting the light from? So we flip the switch and what happens? Okay, you have an electrical impulse, okay, which in the process of hitting the lights causes some heat loss. Okay, so we're losing some efficiency there. And for those of you who are like, not really, leave a light on for long enough, you'll feel it gets hot. Okay, they get pretty hot. So it's coming from the electrical. Well, where did the electrical come from? From the wires. No, we didn't just rub wires together and get electricity, guys. Okay, it comes from mechanical. Where did the mechanical energy come from?
Chemical.
Okay. Typically, it comes from a chemical. The chemical being
Water.
petroleum, okay, or coal. And we're using that to burn something, okay, to cause water to boil, to cause a turbine to turn, which generates electrical energy, which generates light. Each of those stages, we lose energy as heat. That ruins our process. So what we want to try and do is minimize that as much as possible. Okay? For those of you that are more biologically minded, we look in the lower right-hand corner, ATP and ADP. ATP is adenosine triphosphate. ADP, adenosine diphosphate. Remember how the phosphate molecule you looked at, PO4 minus 3? Literally all you're doing is breaking a bond. Well, for those of us that don't know ATP and ADP, why do we care? That's the energy for us to live. It's a single bond. That single bond breaking is enough to cause almost all of our biological functions to exist. That's pretty insanely powerful. That's stored in a chemical bond. That chemical bond is translated into mechanical energy to cause muscles to move, okay, or cause electrical impulses. And you might say, well, that's a pretty efficient system. We don't get any heat loss there. You worked out? Yeah, what happens when you work out? You start sweating because you're generating heat loss. That heat loss is why you're heating up. Okay? We'll pick up with some other stuff on Thursday.